Good morning. This is your Stats Sensei, Mr. Spensei, and this is a warm-up on chi-square. So, scenario one, I'm a loser baby. A nonprofit organization, Hope for Hungry Children, is hosting a charity fundraising event to support families struggling with food insecurity. As part of the event, they introduce a fundraising prize wheel where participants pay $40 per spin to win cash prizes that range from zero, which means they lost, to $100. The wheel is divided into five equal sections. Okay, that's going to be important. With equally likely outcomes. Several donors landed on zero prizes and began to question whether the wheel is actually fair. Worried that trust in the fundraiser might be compromised, the organization investigated and collected data from 150 randomly selected spins. All right, so it spun 150 times. That sounds like right there, sounds like that's a sample size. So N is 150. On an evening in which the wheel was spun 12,875 times. So it looks like we have a population size of 12,750. 12,875, excuse me. All right. So, well, the probability, for sum of all probabilities is one, but we spun the wheel five times. One divided by five is 0.2. So the probability of success or probability of getting to zero should be about 20% of the time. The probability of 10 is 20%. Probability is 20 of 25 is 20%. And the probability of 50 and the probability of 100 are 25 because it's just one divided by five. And if they say it's an equal amount, you're just going to take the number, the number of possible outcomes, and you're going to divide that into one. So one in this case divided by five. Well, this is what they observed. They observed 55 zeros, 30, 10, 28, 25s, 22 50s, and 15 100s. And when we add those up, and we should go ahead and check that out just to make sure, but it should be 150 to represent the 150 spins. So let's do that. So 55 plus 30 plus 28 plus 22 plus 15. That ends up being 150 spins, and there we go. All right, so I'm going to go ahead and enter that information in stat edit 50, 35, 28, 25, 22, and 15. And this is stat edit. And I could just go stat calc, one var stats, and go, oh, some that just means summation. Add up all the x's, I get 150. Go back to stat edit, and we're going to put in those percentages. Now we remember we said it was one divided by five. So we put in 0.2 all the way down. All right, and we're going to go back up to the top of L2, and we're going to calculate our expected values. Well, to calculate the expected values, you're going to have to go expected value equals the sample size times the probability. Well, we know the probability is 0.2, and we know the sample size is 150. So we're just going to go 150 times 0.2. But to do that, we're going to go blue 2 times 150. And there, we end up getting expected values of 30. All right? So, based on the data, can you conclude the wheel is fair or unfair at a 5% level of significance? So we have an alpha level. And it says, answer the following in the space below. Is this a chi-square test of independence or goodness fit? Justify your response and give the expected values. Well, we just calculated our expected values. Our expected values, and I'll highlight those in orange, are 30 because we expect it to be 30 wins for each category because it said that they were equally likely. All right. Now, to be a chi-square test of independence, we have to have one sample with two variables. When I look at this, I go, okay, we definitely have one sample. All right. They select a random sample of 150, but I look at this and it's like, hey, the only variable is the winnings. I don't see any other variable. Frequency is not a variable. All right. Winnings is the only variable. So I only see one sample, one variable, one sample, one variable. It can only be a chi-square goodness of fit. All right. Now, the one thing I want to point out to you is my variable in this case is winnings. And so variables is winnings, and I look at it and go 1, 2, 3, 4, 5 levels. All right. It's winnings with 5 levels. All right. Once again, to be a chi-square fit, it's one sample, one variable. All right. All right. So that tells us that part of the warm up. Moving on, we have another one. Generational genres. A major streaming service is analyzing user data to improve its movie recommendation system. While the platform currently films based on viewing history, excuse me for a second, um, viewing history, executives suspect the movie genre preferences may vary by age group. If a relationship exists, the fact that they mention relationship, probably independence. They could refine the recommendation algorithm to provide age-specific content suggestions, enhance the user experience. To investigate, the service randomly selects 870 users from its more than 5 million customers and asks about their favorite movie genre, action, comedy, drama, or sci-fi. They also record each user's age group. All right, so they come back here and they say movie genre vary by age group. All right. So is this a chi-square test of independence or goodness of fit? Well, first off, when I read the question, they ask me if it's independent. All right, they ask me if it's independent, so I know it's a test of independence. But more specifically, when I look at this, I go, oh, you know what? I happen to have one sample, one sample of 870, but I have two variables. And my two variables are movie genre and age group. All right. And so we have movie, because we have one sample, two variables, that makes us a chi-square test of independence. And being that it's a chi-square test of independence, and we know it's movie genre, how many levels are there? Well, movie genre, we have action, comedy, drama, sci-fi. So we have 4 levels. And for age group or age, what is called age, we also have 1, 2, 3, 4 groups is also. So it's also 4 levels, which is why we have a 4x4 matrix. All right, the other thing we need to do is calculate our expected values. All right, now I know you can see them right there and copy them, but here's how you actually get those. So you're going to go get to a clear screen and you're going to go blue and then look for the matrix button right here, arrow over to edit, press enter. And we just said we have 1, 2, 3, 4. And please note, we do not count the totals. All right. When we're inputting the matrix, we're not counting the totals. So we have 4 rows, 4 columns. So this is a 4x4. And we input those data, the 80, 60, 40, 70, etc. All right. So once you have that in, just like I do, you're going to go blue quit. And while this seems a bit weird, you're going to go ahead and run the test, stat, test, chi-squared test, because this is not a goodness of fit. This is just a chi-squared test of independence. Calculate, and you're like, I still don't see it. And I go, I know. And we're going to go blue matrix and re-enter the matrix. We're going to go to edit, Instead of A, we're going to drop down to B. And now we see our matrix values. All right, now we see our expected values. So that's how you get your expected values. All right, appreciate you watching this warm up. I know it was a little longer than usual, but I hope it helped. Talk to you later. Thanks.